Hey everyone, and welcome back. Before we begin here today, please make sure that you like and subscribe because it really does help out our channel and it also helps us reach others in need of assistance with these topics. So this will be our sixth part in our static series looking at truss analysis using the method of joints. So we just have to solve for each truss member here on this truss shown. So first thing you want to do when you are solving for trusses, which solving for trusses, all that means is that you're finding the force in each member of the truss. So we have 1, 2, 3, 4, 5 members here. So we have to find 5 forces, one for each member. So first thing you want to do, if it's not given to you at the start of the problem, is that you need to find the reactions for your truss. Now, even though it is a truss, you just treat it like any other kind of member where you're finding reactions just using the external forces, which we have 2 kilonewtons here and 2 kilonewtons over here. So we're just going to use those two forces to find the reactions for the pin here at C and the roller here at D. So first thing I'm going to do is I'm just going to sum moments about point C equal to 0. So I'm going to assume my dy is upward. And based upon the geometry here, I'm going to assume that Cy has to be going downward here, because I'm going to assume that this thing is tipping over and Cy needs to pull it back. So I'm assuming this whole truss is rotating this way and Cy needs to hold that down, making sure that it does not tip over. So when you're assuming these directions for these reactions, no big deal if you get it wrong. It just will pop out as a negative answer in your moment equation. That just means you assume the wrong direction. So drop the minus sign, flip the arrow, perfectly okay. All right, so going with summing moments about point C, that would give us dy. So let's go ahead and sum moments here. Taking this first 2 kilonewtons of force, well, its perpendicular distance over to C is 3 meters, and it will be rotating clockwise about C. So I'm taking counter as positive, so it'll be minus 2 kilonewtons times 3 meters. And then this one over here at point B is also rotating in a clockwise manner. So it will be negative, and its distance is a total of 6 meters over 2C. So minus off 2 kilonewtons times 6 meters. And then lastly, I have dy over here, which will be rotating counterclockwise the way I have it assumed. So plus dy times its perpendicular distance over to C, which is 3 meters. And of course, Cy does not count because it goes right through point C. It does not have a distance to point C to itself. So dy is my only unknown in this equation. And when I solve for it, which is pretty simplistic here, dy will pop out to be 6 kilonewtons, and it popped up to be a positive 6 kilonewtons. So that means my assumed arrow direction of up was correct. Alrighty. So now that I have dy, what I can do is I can sum forces in the vertical direction here in the y direction to get C sub y. Well, I will have 6 kilonewtons from dy going upward, minus off 2 kilonewtons, and then another 2 kilonewtons. And then I have C sub y assumed downward, so minus C sub y equal to 0. C sub y is my only unknown in there, so I can solve for it. And it pops out to be a positive 2 kilonewtons, which means my assumption arrow of down is correct. Now, if I would have assumed upward, for C sub y at the start, it would have popped out to be a negative 2 kilonewtons, which means I assume the wrong direction. It has to go downward. Alrighty, well, since C sub y is a pin, it's also may have a C sub x here in the horizontal. Well, I don't have any horizontal forces here being applied, external forces. This is a vertical, and both my reactions are verticals. So there's nothing for the horizontal reaction to react to. So it's 0. All right, so that's your first process, is getting those reactions for your trusses using just standard reaction procedure. Okay, so now once you find your reactions, this is when you're going to start using the method of joints. And the method of joints is where you just look at one single joint, you isolate it out, and you are only concerned with the forces and the members that are acting on or attached to that joint. And typically a good joint to start at is one of your reaction joints. So let's start down here at joint C. So what I'm going to do is I am just going to isolate out joint C, and I'm only concerned with what's being applied at joint C. So I have C sub y, C sub x, this member from AC, and this member DC as well. Alrighty, So member AC is a diagonal member, so it is going to consist of an X and a Y force. And CD is a horizontal member. It is only going to consist of a horizontal force. Keep in mind that truss members, a true truss, is only going to be consisting of axial forces. Diagonals will have a horizontal and a vertical force because, well, it's at an angle. So looking at what we have here, at each joint, we are going to sum forces in the X and Y. So if we go to sum forces in the X first at joint C, what we're going to have is C sub X is equal to 0. I'm going to have this unknown horizontal force of this diagonal up here and an unknown horizontal force for CD. So if I were to sum forces in the X first, I get too many unknowns and I can't solve for anything. Well, looking at what's in the Y, I have C sub Y, which is downward. And then my only other vertical force in the Y direction is this vertical force for the diagonal AC. So what I can do is I can solve for this directly. So by summing forces in the vertical direction, I would have CY, which is 2 kilonewtons downward. So to balance that out for equilibrium, I need 2 kilonewtons in the upward direction here. Okay, so what's the next step here? Because I still don't know anything that's going on here with my two horizontal forces. Well, there is a trick that you can use when you have diagonal forces. The slope of the diagonal force based upon the dimensions has to be equal to the ratio of the forces inside that diagonal. So for instance, your X force for your diagonal divided by the Y force in your diagonal has to be equal to the X dimension of your diagonal divided by the Y dimension for your diagonal. So whenever you get one of your forces for the diagonal, you can get the other just using the dimensions. So let's go ahead and let's set up this ratio here, which I'm just going to put up here. So I'm looking for the X force, which I'm just going to abbreviate it as X dash F, divided by the Y force on the diagonal, which is 2 kilonewtons. That ratio has to be equal to, well, the X dimension, the horizontal dimension, which is 3 meters, divided by the vertical dimension, which is 1.25 meters. So just cross multiply and divide. And then my X force will essentially just be 2 times 3 divided by 1.25. And it pops out to be 4.8 kilonewtons of force here. So now I know that this is 4.8 kilonewtons of force. Okay, well, what about the direction here? Well, once you get one value and its direction for the diagonal, the other one has to match with the slope of the diagonal. So for instance, this slope looks like this. If I scroll down just a little bit here. So I'm going to have something that looks like this. Well, I know that my vertical force at the bottom left here has to be going upward. It has to be pulling away from joint C. Well, since trusses have to be made of axial forces, this diagonal is really only running up and to the right, or it could be going down and to the left. Well, I know that one of them has to be going upwards. So if I were to pick a left arrow here, that means that my resultant force between these two up and to the left would actually be going perpendicularly, or not exactly 90 degrees, but not along the same axis of the diagonal. So because I only have two options here of down and to the left and up and to the right, this is dictated as upward. So that means that I have to be going to the right for my reaction or my horizontal force inside that diagonal relative to joint C. The angle or the slope of the diagonal has to be acting between your two component forces in the X and Y. So since this is going upward, this one has to be going to the right. So what that means here is that this is acting 4.8 kilonewtons to the right relative to joint C. Well, that means that this force in DC and CD has to be countering that because C sub X is 0. So the only other way that this 4.8 kilonewtons can be countered in equilibrium relative to joint C is that we have 4.8 kilonewtons acting to the left relative to joint C. Okay, so we have all our forces on joint C. We just have to complete a few arrows here. So as I said, we are up and to the right relative to joint C. So my arrow can either be down and to the left or up and to the right here relative to joint C. Well, dictating which way my forces are going here, it has to be up and to the right at joint C. Okay, so we have C completely solved for our equilibrium here and our arrow directions. Now, before moving on, what you want to do is you want to complete the arrow direction at the opposite end of the member. So CA is up here. We are pulling away from C. So that means it has to be pulling away from A because pulling away represents tension in the member. And it has to be in tension all the way across if it starts in tension. So looking at CD here, we have an arrow that is pushing on C. Pushing represents compression. So that means it has to be in compression at the opposite end as well. It cannot change from tension to compression until it hits another joint. So we are pushing on C, so we have to be pushing on D. Another way that you can remember this is that the arrow at the opposite end has to be going in the opposite direction as your starting direction. So we have to the left here, at the opposite end, it has to be going in the opposite direction, which would be to the right. That's another way that you could remember it. Okay, so let's go ahead and let's fill out the hypotenuse or the true axial force inside member CA, because the true axial force in D is 4.8 kilonewtons. These are just component forces for CA. Let's go ahead and get the actual axial force inside of CA, which would just be 2 squared plus 4.8 squared and then square rooted. And that gives us 5.2 kilonewtons, and that would be in tension. CD would be 4.8 kilonewtons in compression because the arrows are pushing on the joints. Okay, so that would just be our first joint at C. Once you completed the joint at C, you just move on to a different joint. Now, if you go to another joint, just try to do the same methodology all over again. Only concern yourself with what's being attached to or what's acting on your joint. Now, you may choose a joint that you cannot solve for anything, and that's okay. You just go to a different joint until you find something that you can solve for. It's called joint hopping. You don't have to have everything be in a perfect line where you go in alphabetical order like A, B, C, D. You just go wherever you can in order to solve stuff. Okay, so let's go up here to joint A. So let me scroll back up just a little bit here. So looking at joint A, I am only concerning myself with what is being acted on at joint A. So I have 2 kilonewtons of force. I have member AD, which I don't know. I have member AB, which I also don't know. But I do have this diagonal force here from CA, which consists of 4.8 kilonewtons in the horizontal and 2 kilonewtons in the vertical. And my arrow direction, which is down into the left relative to joint A, which means that I am going to have my vertical force be downward and my horizontal force will be to the left. So this 2 kilonewtons is acting downward at joint A, and 4.8 kilonewtons is acting to the left at joint A. So let's go ahead and use all these forces here, and let's solve for AD and AB. Well, AB is purely horizontal, so summing forces in the horizontal direction, the only force I really have is the 4.8, because the 2 kilonewtons is vertical. This 2 kilonewtons being applied is vertical, and AD is also a vertical. So I would only have 4.8 kilonewtons in the horizontal, which AB has to counter to create equilibrium. Since it is 4.8 kilonewtons going to the left, that means I need 4.8 kilonewtons going to the right. So now my horizontal is complete in equilibrium here relative to joint A. All right, now let's look at AD, which is my only vertical unknown. I have 2 kilonewtons going downward from the diagonal, an applied 2 kilonewtons going downward. So in order to have equilibrium, I need 4 kilonewtons going upward at A in order to have equilibrium. All right, so there are my member forces. Now I just have to complete the arrows at the opposite ends. Well, AB, it is pulling on joint A, so it must be pulling on joint B. This represents tension. Anytime you're pulling on a joint, that is tension. I have 4 kilonewtons, which is pushing on joint A. So I need it to be pushing on the other joint as well. This represents compression. So you can also think of it the opposite end. Well, this is going to the right. The opposite end has to be the opposite direction, which is going to the left. Looking at AD, we have it upward here. Opposite end has to be going in the opposite direction, which is downward. So now AD is complete and AB is complete. Alrighty, so we just have one more member to do, which is DB. So let's go ahead, and what I'm going to do is I'm going to go over here to joint B and look at that. Once again, only isolating out joint B and only concerning ourselves with what is being applied to joint B. So I have a vertical and a horizontal because it is a diagonal. Anytime you have a diagonal, you automatically have a vertical and horizontal force. So looking at joint B, I have in the horizontal here, I have 4.8 kilonewtons, and my only other horizontal force relative to joint B is this one. So since this is going to the left, 4.8 kilonewtons, I need 4.8 kilonewtons, and it has to be going to the right. Well, moving on to the vertical here, I have 2 kilonewtons in the downward direction. This is my only other vertical acting at joint B. So it has to counter that to create equilibrium, and it has to be 2 kilonewtons in the upward direction. So looking at my arrows here, I have this and I have this, which is up and to the right. So relative to joint B, that means that I have this arrow here of up and to the right, which means it is compressing joint B. So it has to be compressing joint D as well at the opposite end because I'm up and to the right here, opposite end, opposite direction, down and to the left. Alrighty, so let's go ahead and let's fill in the actual axial force here. 2 squared plus 4.8 squared square rooted gives me 5.2 kilonewtons of axial force inside member DB. Alrighty, so there is the completed truss. There is all the members solved for, because you can say that CA is in tension, 5.2 kilonewtons. CD is in compression, because the arrows are pushing on the joint, 4.8 kilonewtons. AD is in compression, 4 kilonewtons, because once again, pushing on the joints. 4.8 kilonewtons in tension for AB, because it is pulling on the joints at each end. And then DB is in compression, 5.2 kilonewtons by pushing on each joint. So there's the complete solved truss. Now, what you can do is you can do a last check here because you're going to most likely end up with a joint that you did not work at, you did not use. Well, what joints did we use to solve members? Well, we used C, we used A, and we used B. We did not use D whatsoever. So what we can do is that we can make sure that we have equilibrium being held here at joint D. And if equilibrium is true there, then we most likely have done everything correctly. If equilibrium is not true at joint D, something is wrong somewhere. So let's look at our values here. So let's make sure that we have everything in the vertical direction canceling out. So I have 6 kilonewtons of the upward direction for the reaction. So I have 6 up. I have 4 coming down here for AD. So that means I need an additional 2 coming down in order to cancel with the 6 in the vertical. Well, this is a horizontal. This 4.8 is a horizontal. Well, there's my 2. And the arrow is down and to the left, so that means it's going downward. So in equilibrium here, I would have 6 up, and then I would have 4 down, and then I would have an additional 2 down so that they would cancel, and I would have equilibrium in the vertical direction relative to D. Alrighty, so now let's check the horizontal here. Well, the horizontal, I only have really 2 because everything else is a vertical here. I have 4.8 kilonewtons acting to the right here at joint D. Well, I need 4.8 going to the left to cancel with that. Well, this is a vertical. This is a vertical. The 2 is a vertical. Well, then I have 4.8 kilonewtons here from this diagonal. The arrow is down into the left, which means that my 4 kilonewtons is going 4.8 kilonewtons, sorry. 4.8, we're just going to squeeze that in there, 4.8 kilonewtons going to the left. And yeah, it does cancel with it, and it does cancel out and be in equilibrium. So the horizontal and the vertical at joint D do cancel with each other in their respective directions so that we have equilibrium being held at joint D. So that gives me a good bit of confidence that I've done the entire truss correctly. So showing final answers, what you can do is you can show this. It really depends on who's grading it, right? It depends upon what your professor wants to see. But in real world application, this is perfectly reasonable to show something like this. Or what you can do is you can just simply state like member CA is 5.2 kilonewtons in tension. And then you can say like AB is 4.8 kilonewtons in tension, and you can list all these members out if you want to do it like that, or if whoever's grading this, if this is a homework assignment or test, what they want to see as answers. But that's how you would work this particular truss utilizing the method of joints. So I hope this video was helpful, and if you want to see more problem solve this variety, please check out the other videos on our channel. Also, if you haven't done so already, please like this video, leave a positive comment below, and subscribe to the channel because all of that does help us out greatly. Thank you for watching, and I hope you have a fantastic day.